This is going to be one of the easier lessons I think we cover because we really know everything we need to know. It's just another way of looking at it. Um, so this language, explicit and recursive sequences, explicit is like having an equation, what we've been working with most of the year. Recursive is if I start you with a number and tell you the pattern, you can figure out further numbers, which should kind of sound similar to explicit. It's just a different way of writing it out. Arithmetic sequences, this is what we've learned as linear relationships. They have adding patterns called the common difference. All right. In a linear equation, the common difference is what we would call the slope. So you're already aware of what this is. It's just a different name for when we're having a different conversation. Geometric sequence is what we've been learning this unit, exponential functions. They have multiplying patterns with the common ratio being what we learned is the multiplier, or the b in this y equals a times b to the x relationship. That right there is the multiplier, which is similar to what we're calling the common ratio. And we'll see the comparison between the equations later on. So we were pretty stellar at these on the quiz. Geometric, arithmetic, neither. Well, that's asking you to look for the pattern. Okay, this is going to be a multiplying pattern. This is going to be an adding pattern. And neither is going to be neither. So to get from 120 to 60 and 60 to 30, the only thing that fits that is dividing by 2. And then 30 to 15 is also dividing by 2. You're going to want to check every step. So this is going to be a geometric one. Now I know it's supposed to be a multiplying pattern, but isn't dividing by 2 the same as times 1/2? So that's our common ratio. Our common ratio is 1/2. Now let's look at the second one over here. 2 to 6, that can either be plus 4 or times 3. 6 to 11, that can either be plus 5 or times not an even number. It'd be like 1.83. It's not going to work. So we don't have a working multiplying pattern or a working adding pattern. This is going to be a neither. This would actually end up being some sort of quadratic, which is what we'll learn chapters 7, 8, and some of chapter 9. All right, so we got a geometric here and a neither over here because it didn't have a consistent adding or multiplying pattern. Here's another thing that we can be asked to do with these sequences is find the next 3 terms. We've done this before in the class. First, we have to find the pattern. This one is going 3 to 6, 6 to 12, 12 to 24. Adding definitely won't work, but we were able to find a multiplying pattern. So the next 3 would be 24 times 2 is 48. 48 times 2 is 96. 96 times 2 is 192. Then over here, let's find the pattern. 64 to negative 16. Negative 16 back to positive 4. That's dividing by negative 4. 4 divided by negative 4 is going to be negative 1, so the pattern keeps working. So now we keep going. Negative 1 over negative 4 is just positive 1/4. 1/4 divided by negative 4 is going to be like 1/4 times negative 1/4. If we multiply straight across, we get, so here's one of our answers. The next answer will be negative 1/16. Then if I do it one more time, times negative 1/4, the negatives are going to cancel out. And the 16 times 4 on bottom is going to be 64. So it keeps alternating between negative and positive, but now the denominator is getting bigger by 4. So an easy way to divide by a number repeatedly once you have a fraction is just keep multiplying the denominator by that number. All right, So try not to struggle with the fractions too much. I'm trying to give you strategies to work with them. You can either treat the division as multiplying by a fraction, or you can remember the rule that if I divide by a whole number, I can just multiply the denominator by that number. A couple ways to think about it, but let's compare the difference between a linear and an arithmetic sequence. Then we'll do an exponential one as well. The reason I wrote these equations on top of each other this way is because the information means the same thing, just in different vocabulary. So y and a sub n, this is called a subscript, so you typically say that as a sub n. So y and a sub n are the result when we plug in a number. So that's the result or output. So if I want to know the 36th term, I would use n equals 36, or up here, that would be finding the value of y when x equals 36. Y and a sub n would give us the result of plugging in 36 as a number. So these are the results. M and d, this is the slope or the common difference. This is essentially my rate of change. It's what I'm changing by every time I increase x by 1 or n by 1. This is what comes out as our adding pattern, slope and common difference. Both of those can be generalized with the word rate of change. X and n minus 1, this is the input. This is the information we supply. And then b and a sub 1, this is the start value. So b is the y-intercept, which is when x equals 0. A sub 1 is the first term in a sequence. So a sub 1 isn't when n equals 0. That's because in a sequence, you usually refer to your first term as your start term. You don't usually have a 0th term, if that makes sense. So now let's look at geometric sequences as well on top of the a times b to the x equation. So here's exponential and geometric. Some of these things are going to be the same. Y and x are still output and input. So again, if I plug in a value for x and want to see the result, like if I want the 40th term of a geometric sequence, I would put 40 in for my x or my n minus 1, and whatever comes out for y or a sub n is the result. So those mean the same information. A and a sub 1 are both going to be my initial value. A sub 1 specifically means the first term, but in a sequence, the first term is our starting point, so it should still be the initial value. So just like last time, each of these things is a reflection of what we already know. B and R are what we know as our multiplier. Common ratio is the multiplying pattern. B is our multiplier. They can both be described pretty well as the multiplier. So these equations are really the same. We just need to be able to read them. An example of how to use this, let me write that word better. Write an equation for the nth term of this sequence, then find a sub 10. So that would be the 10th term. So we're going to look and check what kind of sequence it is. 2 to 12 is times 6. 12 to 72 is times 6. So this one's going to be geometric, not linear, because it's a multiplying pattern. So by doing this, we've already found our common ratio. So that's our b value. Our common ratio is what we usually think of as our b value. But now the equation we have to keep in mind is a sub n, the nth term, equals a sub 1, the first term, which the problem shows us right here, times r, which we already found, to the n minus 1 power. All right, so the stuff we need to find to fill in, are a sub 1 and r. And then later on, when we want to find the 10th term, that's what we'll plug in for 10. So r is 6, a sub 1 is 2, that's all we need. A sub n equals 2, our first value, times 6, our multiplier or common ratio, to the n minus 1 power. So now if we want to find the 10th term, we would plug 10 in for n. A sub 10 equals 2 times 6 to the 10 minus 1. And what's 10 minus 1? That should be easy. That's 9. So I'd have to multiply by 6 9 times. Had to grab a calculator quick. Comes out to 20,155,392. So you can either multiply by 6 repeatedly, or you can type it in as 2 times 6 raised to the 9th power. Make sure you follow order of operations on your calculator if you do that. One more notation to learn. I know we've covered a lot of these today, but a lot of the letters mean the same thing. So just try and keep translating for yourself. A lot of math ends up being kind of like reading a new language. So the better you keep up with this stuff, the easier it is to learn new things that use it. So a recursive rule gets you a new term depending on the previous term. So it's actually a very simple idea. So we still have the common ratio or the multiplier, and we still have the common difference or the rate of change, slope, the adding pattern. So the only difference between an arithmetic and a geometric sequence, like we've been discussing this whole time, is whether it multiplies or whether it adds. So a sub n minus 1, that's the previous term, and a sub n is the next term. So the next term relies on the previous term. So that's what these subnotations mean. And that a sub n minus 1 means the same thing for arithmetic as it does for geometric. So I can just draw arrows over here and it still applies, which is nice for us. So let's look at what some recursive sequences look like. So if someone tells me a1 equals 2, and then they give me the recursive rule, a sub n equals a sub n minus 1 plus 3, they're telling me that every next term is the previous term plus 3. Let's read that as a sentence. Every new term is 3 more than the previous term. Understand that that's essentially a sentence that means this using math language. So if our goal is to find the first 6 terms, and they start me with 2, I would do 2, add 3 is 5, add 3 is 8, add 3 is 11, add 3 is 14, add 3 is 17. 6 terms, done and done. The way I know that is I did 3 more than the previous term. This is what they mean by a recursive rule. It's not an equation, so it's hard for you to just say, find me the 36th term. That's a little bit hard to do, which is when writing a sequence or an equation is better. But this is about being able to read recursive rules. What's happening each new time? Same thing with a geometric one, but with multiplying. So let's look at a multiplying version. So a1 equals 1. And then a sub n, each new term, is 3 times a sub n minus 1, the previous term. So each new term is 3 times the previous term. So my multiplying pattern is times 3. Gosh, that glare's really getting in the way. I gotta get something to block that. I always say that and never do. So here for my first 6 terms, I start with 1 times 3 is 3 times 3 is 9. 9 times 3 is 27. You might need a calculator for the next couple. 27 times 3 is 81. 81 times 3 is 243. So there's my first 6 terms. And the way I did that was each new term was 3 more than the one before it. So that's a recursive rule. That's how we would use something like that.